Hello, and thank you very much for attending this presentation. I'm Armin Kieberle, working at the University of Kassel in Germany. In the following, I will summarize part 2 of 20 years of swim start research at the University of Kassel, mainly concerning a new and detailed model of swim start performance, which was developed in the course of the PhD thesis of my assistant Sebastian Fischer. At the end of this presentation, I will talk about the project to optimize the swim start posture on the block before the start, and I will talk about a project using artificial intelligence for a markerless analysis of all the videos of German elite swimmers when being tested in a flow channel. In the course of his PhD project, Sebastian analyzed swim starts to 25 meters, respectively 50 meters, sprints of 46 elite female and male German swimmers. Their personal best times were within 7% of the corresponding world records at the time. They were all among the top 3 swimmers in the German swimming championships. There were 6 participants of Olympic Games, 2 world record holders, and 8 European record holders. For the kinetic data acquisition, again, our portable force measurement starting block was used. For the kinematics, 4 video cameras, 2 above water level at 1 meter and 3.5 meters, and 2 below water at 7.5 meters and at the 15 meters were used. For the statistical data evaluation, a Lisrel structural equation model was used to analyze the explained variance of grab start and track start performance and entry behavior. Here is the list of variables analyzed. Block time between the starting signal until takeoff, horizontal center of mass displacement during block time, vertical center of mass displacement during block time, average horizontal and vertical velocities on the block, flight time between takeoff and first water contact with the fingertips, flight distance as horizontal center of mass displacement between takeoff and first water contact with the fingertips, vertical and horizontal center of mass velocities at takeoff calculated by the data from our portable force measurement block, relative center of mass height at takeoff calculated by the vertical center of mass displacement between takeoff and the first instant of water contact, water time between first water contact following the flight phase and head passage at 7.5 meters, water distance as horizontal center of mass displacement during water time, average below water center of mass horizontal velocity as calculated by water distance divided by water time, average center of mass horizontal velocity during the water entry phase as horizontal displacement between the initial water contact of the fingertips and the instant of feed-in divided by the corresponding time, average center of mass horizontal velocity in the glide phase as horizontal center of mass displacement between instant of feed-in during entry and the head passage at 7.5 meters divided by the corresponding time. Using the swim start data of the 46 German elite swimmers in a Lisrel path analysis, explained variances for the track start were 97.9% and 99.1% for the start time and the glide time, 69% for the block time, and 87.8% and 97.7% for the average horizontal center of mass velocity in the glide phase and the horizontal center of mass takeoff velocity as indicated by the red circles. In addition, arrows pointing to these criterion variables show the path coefficients as indicators of the strength of the prediction for the target variables. Overall, the path analysis model provided a high external validity as indicated by the p-close value. For the grab start, Explained variances were 99.9% and 99.2% for the start time and the glide time, 69.8% for the flight time, and 84.5% and 99.5% for the average horizontal velocity in the glide phase and the horizontal center of mass takeoff velocity on the block, as indicated by the red circles. Again, the path analysis model for the grep start provided a high external validity as indicated by the peak close value. The most important results of the path analysis with the Lisrael structural equation models were: gliding time is the most important predictor of swim start performance. This result corresponds to the early findings of Hay in 1985. The average center of mass velocity underwater has a stronger impact on underwater time than the distance traveled underwater. The results of the structural equation models show significant differences between the track start and the grep start. Therefore, there is statistical evidence for specific factorial structures of both swim start techniques. According to the structural equation model results, different magnitudes for the path coefficients in this block time were found for both swim start techniques. In addition, differences in the takeoff posture led to differences in the factorial structure of the flight distance. Horizontal and vertical center of mass velocities strongly determine subsequent swim start phases. Overall, it appears that entry behavior has so far been underestimated as an important determinant of swim start performance independent of the swim start technique. For the entry behavior, various study results in the literature exist, indicating the strong influence of the water entry phase on swim start performance. However, in contrast, there is no study that provides direct information on how the entry should be carried out exactly. Results on the glide behavior and optimal water entry depth are provided by various authors. However, there are no studies in the literature showing an improvement in swim start performance through specific swim start training. A possible explanation for this finding can be attributed to a lack of detailed parameters to capture water entry. In fact, entry technique has been hardly analyzed in scientific studies. The existing knowledge about entry behavior refers, at best, to the angle of water entry. However, there is no consensus among researchers on how to evaluate the angle of entry. Furthermore, there is no clear scientific evidence on the advantages of pike dives or flat dives. Overall, it appears that the entry behavior has not been sufficiently studied yet. Most importantly, there are no kinematic assessment methods in the literature to study the entry characteristics. In Sebastian's dataset, 23 parameters were analyzed to characterize the entry and transition phases. For the kinematic analysis of the entry parameters, a new detection method for the body landmark kinematics during water entry was applied, using 2 video cameras below water. For statistical purposes, relevant input parameters were identified using a principal component analysis with a rotated component matrix. Then, a multiple regression analysis was conducted with the stepwise inclusion of independent variables. Finally, a cluster analysis was used to identify differences in the entry strategies of the German swimmers analyzed. There are 2 main problems to be solved prior to a detailed analysis of the entry behavior. First, how can we analyze kinematic data during entry when vision is distorted by air particles carried along the body surface? Second, How can we estimate the water displacement during entry, meaning the loss of kinetic energy during water entry through water displacement? First, this slide shows a typical image of an underwater view during water entry with a distorted vision as air particles are carried along the body surface. As a consequence, the endpoints of the body segments are difficult to see. However, the orientation of the body segments seems quite clear. Therefore, instead of assessing segment endpoints, segment midlines were assessed using a regression method where 4 data points provided sufficient precision. A cubic spline regression was used for the trunk. Body joint coordinates were then assessed by the intersection of the regression lines or the cubic spline graph. In order to validate this method, the segment lengths of the subjects were compared in and out of the water, showing sufficient precision for the new landmark detection algorithm. To estimate the displacement of water volume during entry, the horizontal length of the entry hole from a lateral perspective was measured through the video analysis. Based on these new characteristics of the swimmer's entry and transition behavior, a principal component analysis with rotated component matrix was used to identify the most important performance factors in the water entry phase. The Varimax method was used to maximize the variances of the loadings between the factors. 7 important factors were identified, explaining a total variance of 87.6%. The most important factor corresponded to the duration of the entry phase, explaining 26.4% of the total variance. The next most influential factor concerned the hip action at entry, explaining 19.5% of the total variance. The third factor related to the redirection time in the entry phase, which explained 16.2%. Factor 4 referred to the diving depth, which explained 7.6% of the total variance. A factor related to the horizontal entry velocity explained 6.7%. Factor 6 corresponded to an estimate of the water volume displaced during entry, which explained 5.9%. Finally, factor 7 for the dolphin kick in the leg explained 5.3% of the total variance. The subsequent cluster analysis was used to identify different entry strategies. In this table, the mean cluster loadings and F-values in ANOVA are shown. Using the 7 most important factors from the principal component analysis, 3 cluster solutions were found. Here, for 4 factors, only significant F-values were found in an analysis of variance for the cluster factor. These were the duration of the entry phase, the estimate for the water volume displaced during the water entry, the hip action during the entry, and the redirection time during the entry phase. Male and female swimmers differed in their entry strategy in terms of duration of the entry phase, displaced water volume, and redirection time during the entry phase. See leftmost column. Finally, a linear regression analysis was used to assess the explained variance of the entry performance. Only those variables are listed in this table with F-values larger than 0.1. These were, in the first table column, the duration of the entry phase, the mean horizontal center of mass entry velocity, the diving depth, and the estimate for the displaced water volume during entry. corrected R-square values on the right representing the coefficient of determination increased from 25% explained variance with the duration of the entry phase only to 49% explained variance using all four of the above highlighted factors. This graphic shows three poses for each of the three entry strategies detected by the above cluster analysis, which are a flat dive strategy in green, a pike dive strategy with a delayed redirection movement in blue, and a pike dive strategy with a short redirection in red. The two swimmers shown in the left and the right video indicate a more pike-like entry strategy with a short redirection and a powerful leg-kicking action. Here, the relevant movement features for the entry behavior refer to a hyperextended back at the center of mass water entry, followed by an active leg kick indicated by a flexed knee joint shortly after the swimmer is fully submerged. Overall, our main findings relate to a significant correlation between the duration of the entry phase and swim start performance as measured by the time difference between the start signal and the passage of the head at 7.5 meters. Longer entry phases correspond to shorter swim start times. In addition, higher mean horizontal entry velocities also correspond to shorter swim start times. There is a tendency for the swim start time to correspond to the dive depth and a displacement of water volume during the entry phase. All four predictors explain approximately 50% of the total variance in swim start time. The entry strategies differ in hip angle at water entry, redirection behavior, duration of the entry phase, and volume of water displaced during the entry phase. There is a tendency for differences in entry strategies to correspond to the mean horizontal center of mass entry velocity and the amplitude of the leg kick. Male and female swimmers show differences in the duration of the entry phase. In addition, the sexes differ in the volume of water displaced and in the redirection behavior during the entry phase. In another study, the results of which were presented at the 12th International Symposium on Biomechanics and Medicine in Swimming in Canberra, Australia, we investigated whether elite swimmers' stance positions on an OSB 11 block prior to a track start could be improved by making small changes in different directions. We had hypothesized that swimmers' individually preferred stance would not necessarily be optimal in most cases. The idea was to systematically change their step length, their center of mass height, and front or back leg weighing based on their preferred stance position. For example, the center of mass height relative to the individual leg lengths was 0.72 plus minus 0.04 leg lengths for the females and 0.73 plus minus 0.04 leg lengths for the males. Furthermore, the relative step lengths expressing the horizontal distances between the toes of both feet were found to be 0.66 plus minus 0.07 leg lengths for the females and 0.63 plus minus 0.08 for the males. For the present study, the standard deviations were reconverted relative to the sex and leg length of each subject. These standard deviations were then added or subtracted from the preferred stance configurations. See left image. For example, a low center of mass height for a subject was determined by their center of mass height in the preferred stance position minus one standard deviation reconverted to the subject's leg length. Thus, in addition to the preferred stance, 8 configurations were possible for each leg. center of mass height low versus high, center of mass distance rear versus front weighted stance, and stance width narrow versus wide. However, due to the demands of motor coordination, only 4 of the 8 possible configurations for each leg could ultimately be maintained on the block. These configurations were narrow stance with center of mass position high anterior, number 1, wide stance with center of mass position high back, number 2, wide stance with center of mass position low front, number 3, wide stance with center of mass position low back, number 4. Swim start performance assessed as a time between the start signal and the head crossing at 7.5 meters was assessed in 2 trials for each swim start position in a randomized order. This table shows the frequencies of swim start improvements according to postural changes for the preferred stance position. Of note, regardless of preferred or non-preferred forward leg, 8 out of 19 swimmers showed improvements in swim starts when the center of mass position was changed to high and forward with a narrow step length. For a smaller number of swimmers, other changes also proved beneficial, such as a low front center of mass position combined with a wide step length. Overall, there was no systematic tendency towards the universally best swim start position. There was a tendency for a narrow step length in line with a large center of mass height leading to the most improvements. For 9 swimmers, putting the preferred leg forward improved the swim start. For 11 swimmers, putting the non-preferred leg forward improved the swim start. For 9 swimmers, improvements in the swim start performance were found in stances other than the preferred one. 6 of these 9 swimmers, 30%, improved their swim start performance up to 15 meters after the block. 4 swimmers improved their swim start performance in 1 other posture and 2 other postures respectively. 2 swimmers improved their swim start performance in 5 other postures. And swim start performances were found in 3 swimmers, either in 6, 4, or 3 starting positions other than their preferred one. The aim of this service research project was to use artificial intelligence to develop target movement technique models for the different strokes in swimming based on flow channel videos of the best German swimmers over the last 3 decades. In other words, a target movement technique including the movement features of international top-level swimmers. In the first step of the study, videos of the best German swimmers of the last 3 decades were examined for their suitability for a fully automatic artificial intelligence detection algorithm using state-of-the-art deep neural networks to determine the coordinates of the body segment endpoints. The neural networks were then trained and tested in a previous research project using data from other swimmers in the flow channel. Here are the different steps of our analysis. Using deep neural network algorithm, 2D coordinates for the 14 body segment endpoints, ankle, knee, hip, wrist, elbow, shoulders, center of the neck, and the cranial end of the head were detected. The location of each segment endpoint was determined by the X and Y coordinates for each video frame, such that each individual pose could be represented as a 28-dimensional vector encompassing both sides of the body. For the butterfly stroke and the backstroke, approximately 2 to 3 seconds were needed to cover 2 cycles. Therefore, the video frame rates were depicted between 100 and 180 individual images, and thus 100 to 180 individual poses for each swimmer. In the next step, the resulting 2D coordinates were compared to the video images to find out about erroneous segment endpoint detections. For those cases, segment endpoints were manually corrected. In this slide, the differences between the true 2D segment endpoints and the results of the AI detection algorithm are shown. A tendency is visible such that larger deviations were observed for the segment endpoints in the trunk as compared to the extremities. In the next step, a principal component analysis was used to reduce the numerous coordinates of the swimmer's stroke movements across the individual poses to the most prominent technical movement characteristics detected by the main components of the PCA. For this purpose, the eigenvectors and eigenvalues of a matrix consisting of the individual poses were determined over 2 stroke cycles, meaning 28 body landmarks times the number of individual poses. This resulted in 5 main components for the butterfly stroke and the backstroke technique, which together explain over 98% of the total variance of the pose sequences. In this slide, the 5 components for the butterfly stroke style in blue and the backstroke style in red are displayed. When all 5 components were added together, over 98% of the total variance in the poses could be explained. As swimming is a continuous motor skill, the temporal behavior of the 5 components can be modeled using simple sinusoidal functions. Each sinusoidal function is characterized by its frequency or period, its amplitude, and its phase. From these 3 characteristics, it is possible to derive functional values for all 5 main components, which describe the temporal behavior of the mean swimming motion with a high degree of correlation of 97.4%. A double sign function with 6 parameters was used for our analysis. The collection of these function values represents a further step in the data reduction, as the eigenvalues of the main components can only be replaced by 6 parameters per main component when the previous function is taken into account. The next step was to create a matrix structure to store the load coefficients and assign function values for each swimmer. A vector was then created containing the following information on the position of the swimmer, the individual swimming technique, and the corresponding temporal pattern. The advantage of this representation is that it can be transformed. In this way, it is possible to derive an average swimming technique based on the individual movement patterns, which characterizes the greatest possible similarity between the top German swimmers. In a third step of our analysis, the matrix structure was used to identify further characteristics of the movement techniques. For this purpose, another PCA was performed with the normalized values for the previous matrix structure of the swimmers. Based on the mean movement technique, the most important criteria for differences in the movement technique could now be identified. A subsequent linear discriminant analysis was used to test the differences between the technical characteristics derived above, highlighting relevant and irrelevant characteristics. Discriminant analyses are ideally suited to classify between groups, including information on the year of video recording, gender, swimming velocity, height, and weight. For the differentiation between men and women in the backstroke, the gender of the swimmer can be derived with a 73.3 accuracy from the first component of the principal component analysis across the top swimmers. Only 2 men and 2 women from a group of 15 videos were misclassified. This is remarkable, as there are no gender-specific movement techniques so far reported in the literature. In a further step, linear discriminant analysis was used to identify differences between the prototypical 100-meter and 200-meter strokes of male and female swimmers. In other words, for the first time, movement techniques were determined as a function of swimming speed and gender using German elite swimmers' data. On this last slide, you can see a superimposition of the technical model for the backstroke, male 100 meters, and the video display of an elite swimmer at the swimming speed of 1.8 meters per second in a flow channel. There was a 95.6% match with the newly developed digital adaptive technical model. Thank you very much for your interest. This was the second part of our 20 years of swim start research at the University of Kassel.